Well, thanks so much for coming. I hope I don't make a complete mess of this, because I was up at 1 o'clock this morning, still on UK time, and busy doing more slides, because I wanted to cover quite a lot. And then I ended up with 50-odd slides. Normally it's about 25, so I had to cut them all down. So you may find me starting to speed up, because I really want to make sure that there's 5 or 10 minutes at the end where we can do questions and answers. Anyway, so what am I trying to do? DACs are very, very complicated devices, and it's very difficult to explain it. This seminar will be quite technical. I'll try to make it as simple as I can, but you have to talk about the technicalities in order for you to understand things. One of the reasons for doing this talk about DACs in general, in terms of different topologies, is a lot of manufacturers create myths that don't actually make a lot of technical sense. So I'm trying to educate you so that you can understand what's actually going on. And hopefully if you understand, you'll make better judgments in the future. So I'm a little unusual in lots of ways, a lot of my friends would say. But from an electronics point of view, I'm an analog design engineer as well as a digital design engineer. And that you don't normally get. You normally have an analog guy and a digital guy. The digital side of things is something I've learnt since the mid-1990s in terms of actually FPGA design and that kind of thing. Also, I've worked with major silicon companies where I've sold my IP to them and worked on half a dozen different chip projects, as well as designing high-end audio. With high-end audio, I've probably designed about 50 different DACs. I've lost count of how many DACs that I've designed. And I've been working with Chord for just over 25 years. So this is a relationship that it's been going, for quite some time. But I am completely independent of Chord. So when you're buying one of my designs, it's my intellectual property. So firstly, I just want to introduce about clock jitter, because a lot of people talk about femtosecond clocks, and therefore a femtosecond clock must be better than a picosecond clock. This is meaningless, and the reason it's meaningless is because different DAC architectures have different sensitivities to jitter. So it really makes no sense. You need to be talking about the DAC architecture, not the jitter numbers. The jitter numbers, they normally quote a cycle-to-cycle jitter, and that only tells you half the story, because it's, in terms of sound quality, that is the least important problem. It's the low-frequency jitter characteristics, which they don't talk about, and that's the things that actually changes the sound quality. Just to give you an example, there was one project I was working on where we had a spec for 4 picoseconds worth of input clock jitter, and it had to be 120 dBs worth of dynamic range. So I did a design for them, got it working on simulation, it met 120 dB. Then they turned around and said they wanted 15 picoseconds because they thought that the internal jitter levels on the chip would be much higher. So that was fine. You just redesign the DAC itself, and out pops 120 dB with 15 picoseconds. So how you react to a given jitter level depends on the design of the DAC itself. Another problem with clock jitter is that the numbers that people are quoting as the output from the oscillator. It's not what's going on inside the chip. Inside a chip, whenever you have a logic change, a buffer or anything, you're going to add an extra picosecond worth of jitter. And as it propagates through the device, each level that you're creating is going to create more jitter. Another major problem is the actual switching devices that you're using on the DAC. Because it's all very well having a master clock that's really low levels of jitter, but if that's going through a switching device that switches in microseconds, that's where your problem is, not the jitter level that's going into the device. Just one quick thing, external clocks are a crazy idea. The reason they use external clocks is it's something that happens within the pro business. Because in the pro business, you may have 64 A to D converters. They all need to be synced up on a common word clock, so you have a clock source that's separate and feeding through each individual one. The trouble with having a high-end DAC that's feeding an external clock is that clock is going through output buffers, it's then going through a cable, it's then going into an input buffer, it's then being converted into the DAC itself, and that is going to create huge amounts of jitter. So having external clocks is not a good idea. So why do people like external clocks? One of the problems with an external clock is to make your jitter levels better, you need to use a phase lock loop. The downside to a phase lock loop is that you can improve your cycle-to-cycle jitter, but you'll degrade the low-frequency jitter. That makes fundamentals get much wider. That's a form of noise floor modulation. That makes it sound brighter, so you think it's more impressive. So, chip DACs. We had tremendous trouble in designing chip DACs. The problem you've got is that there's a common substrate. A substrate in silicon has got an impedance of about 3 kiloohms. That means that noise from the digital side, will corrupt the analog side. That noise is signal correlated, that will create distortion. It will also create noise floor modulation. So this is a problem that you cannot eliminate with chip design. It's something you can ameliorate and work very hard on reducing, but it's not an issue that you can eliminate. The other problem is that silicon devices, resistors are nonlinear, capacitors are nonlinear, and these are particular issues with chip design. So let's get on to the meat of what I'm trying to talk about. We've got two fundamental types of DACs, R2R or ladder DACs, or delta sigma DACs. With R2R DACs, you have an array of resistors and a bunch of switches, and you control the output from sorting out the switches. Delta sigma, on the other hand, there are two basic types of delta sigma. One is 1-bit output, which is DSD, and the other is a multibit output. The good thing about R2R DACs is that to create your own R2R DAC is not too difficult. It's very, very difficult to get good measured performance. In fact, extremely difficult to get good measured performance. But with a bunch of matched resistors and a bunch of FETs, a designer can create their own R2R DAC. Creating delta sigma DACs is much more complicated because you have to design digital logic, you have to know about FPGAs, and this is an order of magnitude more of a difficult problem. Now, delta sigma DACs have very different topologies, and to say a delta sigma DAC sounds a particular way and say that all delta sigma DACs sound the same, that is incorrect because you've got so many different flavors of delta sigma DACs. I'm not going to be talking in every single flavor that you can get. I'm going to be talking about the broad brushstrokes of types of delta sigma DACs that you've got. So firstly, let's talk about R2R DACs. These use switches to switch resistors. So we've got different values of resistors, and these switches here are with FETs. The output of the resistors creates a current which goes into an I to V converter. An I to V converter is what they call a virtual ground, or it's a current to voltage converter. And this creates an output voltage, which is the signal that you actually want. The problem with FETs is that to get them to be significantly low impedance, and you need low impedance because of noise, means that there's a lot of gate capacitance and intrinsic capacitance within the FET. When you switch the device, you're going to get glitch noise coming through onto the output, and that glitch noise will end up on the output itself. The main problem you have with R2R, there's two basic problems. One is you need the resistors to be matched, otherwise your linearity will be off. The other problem is this glitch noise from the FETs. And that causes distortion and noise. It also means that you're limited with R2R DACS in that you can only run them at 16 times oversampled. You can't run them at 104 megahertz like I do with my DACS. So your transient reconstruction will be limited to microseconds rather than nanoseconds, which is what I can do with pulse array. The other issue is the matching problem. And I managed to find something, 2 o'clock in the morning, someone had done a plot of a 4-bit R2R DAC, which is the same one as I had it earlier. And this is a monotonic R2R DAC. Monotonic means that as you increase the output, the level increases. And you want it to be at least monotonic, otherwise you're wasting your time. The problem you've got is that the transfer function, that means the rate, the relationship between the input and the output, has these knee points here. Now this transfer function actually works when you're using dithered signal on an R2R DAC. These knees, if you do a differential or transfer function, you'll find that the differential goes to infinity because it's a very, very sharp change. That sharp change creates high-frequency distortion. In fact, the distortion will go up to infinite frequencies. What's interesting about this is that there's other things that we have that have got sharp knees, which we know is bad, and that is Class B output stages. And a Class B output stages also has these sharp knees, and they also create very high amounts of high-frequency distortion. The other issue we've got is that as the signal level gets smaller, the distortion gets larger. That is completely the opposite of the way that the ear and the brain functions. Normally, the ear gets more non-linear as the level goes up. It's very linear at small signals, and this is the complete opposite. And that causes problems with soundstage and detail resolution, and makes things sound harder and brighter than they should be. So I've talked enough about R2R DACS, and you can see I'm not a fan. So delta sigma DACS. Delta sigma DACS have got something called a noise shaper and an analog output stage. And the analog output stage will consist of a number of switches plus your filter and the op amps and the analog outputs. The noise shaper takes your digital data, which may be 32 bits or whatever it is, and converts it to a smaller number. For a DSD, it'll convert it to 1 bit. For a normal multi-bit, it will convert it to, say, 5 bits. So then that will control the switches directly, which is part of your DAC function. What the noise shaper does is that if you were to take a 32-bit signal, truncate it by removing the bottom bits and just leaving you with the 5 bits of MSB, you would end up with horrendous amounts of distortion and noise. I mean, you're probably talking about 40 dBs worth of distortion and noise. What the noise shaper does is it looks at the output, compares that to the input, magnifies the error, and then from that magnification or the gain of the error, it will then adjust the next output and it's constantly iterating and trying to improve on the performance to get back to the pure signal. And it does this, of course, by running at a very much faster rate. So noise shapers have got an input subtractor, and the subtractor is the delta of delta sigma. It's then followed by a set of integrators, and the integrators become the sigma, and the integrators are amplifying the error. The output from the integrators is then fed into something called a quantizer, which is just losing the bottom bits that you can't use, and that creates the data. If you want distortion-free performance, you need to add an appropriate level of dither into the quantizer. Otherwise, you get distortion coming through. Performance of the system is determined by the output bit depth, the number of switches that you've got, how many integrators you've got. That's called the order of the delta sigma modulator. And the integrator coefficients, because the coefficients will set the gain, and that will set the amount of feedback that you've got. And of course, most importantly, how fast the actual noise shaper is working. So if the noise shaper works very, very rapidly, going backwards and forwards, it'll get to the correct result in a much faster time, and it'll get to a much more accurate result than if it's doing it very slowly. So noise shaper design is actually very complex. Some people will say it's just maths. It's not, because if you're worried about sound quality and performance, it's actually a non-linear system, and you have to tweak the different coefficients and tweak your architecture to get the best performance. You can design it with MATLAB, and you'll get good performance, but you won't get the best performance as possible. So the speed of the noise shaper is crucial. So if we take a 7th order noise shaper and double the speed of the noise shaper, we'll get a 42 dB, or up to a 42 dB improvement in distortion and noise within the audio bandwidth. But not only does the distortion and noise improve, but the small signal accuracy improves as well. And that's very, very important, the small signal accuracy. If we increase the speed by tenfold, we get 140 dB. And if we went from 3 megahertz to 104 megahertz, you're looking at 210 dBs worth of maximum improvement. So why don't we just keep increasing the speed? The problem we've got is that we've got analog switches or some kind of switching arrangement on your outputs. And if we go too fast, we'll find that the distortion level starts to increase. And that will then damage your measurement results, but it will also damage the sound quality. So there's an optimum point at which the speed of the noise shaper against how fast you can create your analog section depends. And each design will have its own optimum set point to it. And it's like most things in life, it's a question of balancing conflicting factors. And this is something that happens a great deal when you're designing. You want to balance something against something else, and there's different conflicting factors. And often I see something on Headphone, somebody making a comment about something X, Y, Z, and they just don't understand, the conflicting parameters that are going on with this. So why don't we just keep increasing the order? In other words, just add more integrators. The problem with that is if you add an extra integrator, you have to reduce the speed of the integrator. And it exponentially grows, and eventually you'll get to a stage where the integrator is actually contributing nothing in the audio bandwidth. So there is an optimum point on the number of integrators that you're using, because eventually you get to a point where it's making no tangible difference to performance. So, DSD. Now, I talked earlier about R2R DACS having problems with mismatch. and that creates lots of high frequency distortion. The beauty of DSD is that solves that problem because there's only one element. So there's nothing to mismatch. And indeed, when you look at DSD, if you do a distortion plot, you'll find that distortion at minus 60 dB starts to completely disappear. And as the signal gets smaller, the distortion disappears. That is the same way that the ear behaves. So it's completely the opposite to R2R DACS, whereas the signal level gets smaller, your distortion level gets larger. But DSD's got a problem, and the problem is that it's 1 bit. When you're designing noise shapers, a noise shaper likes to go either a little bit too high or a little bit too low, so it needs overload. If you just limit it to +1 and -1, there are times when the noise shaper is saying, I want to be +2, and it cannot be +2. What will then happen is there'll be internal overloads, or it'll go unstable in the worst case, but the noise shaper will misbehave and it won't behave appropriately. The problem with this is this will create noise floor modulation, and we know that with DSD-64, for example, you're looking at 115 to 125 dBs worth of noise floor modulation. That might sound like a small figure, but it's actually an enormous figure in terms of sound quality, particularly as I've been hearing stuff at minus 350 dB in terms of noise floor modulation as still being audible. So this is a huge problem. The other issue is that you cannot use dither on the quantizer, so that in itself will create high frequency distortion problems with DSD. Also, because it runs a fairly slow rate, it has measurable fundamental linearity problems. That degrades perception of depth. For example, DSD-64, the noise shaper performance is around minus 126 dB, which is not that good. The other big issue with DSD is that it's got problems with high-frequency transients. The benefit of DSD is you don't need a sync interpolation filter because it's just the original data. You don't need a complicated interpolation filter. So you don't need an M-scaler. You don't need to worry about those kind of issues. The downside is that large amplitude signals get through the 1-bit quantizer faster than very small signals. What this means is that a small amplitude transient will take longer to come through than a large amplitude transient. So this is another form of transient reproduction problems. This is the reason why DSD sounds a little bit soft and warm, because the transients are not being properly reproduced. And when that happens, the brain cannot make sense of transients, then things start to blur and things just sound softer. Another issue is something called idle pattern noise. This depends very much on the analog section of the DAC, and that's a major issue. You also need to be very careful on your filtering, because 100 kilohertz, you're looking at minus 20 dBs worth of distortion and noise. That's a horrendous problem for analog electronics to cope with. So, let's get on to multi-bit outputs. Now, a multi-bit output delta sigma DAC is the same as DSD, but it's got multiple levels. And it eliminates the noise shaper noise floor modulation problem, because if the noise shaper decides it wants to go to +2, it can. It can go +2, down to 1, down to 0, and it's got the freedom to breathe, as it were. That means it's completely stable, and under all circumstances, the behavior of the noise shaper, if your coefficients are correctly selected, will be consistent. That means if it's consistent, you won't get noise floor modulation problems. Multibit gives better performance because clearly you're increasing the number of bits. If we had a multibit that ran at 32 bits, we wouldn't even need a noise shaper. So increasing the number of bits you've got available will improve your innate resolution. Increasing the number of bits reduces jitter sensitivity. I mentioned earlier about clocks, and my solution to that problem of going from 4 picoseconds to 15 picoseconds was to increase the number of elements within the DAC design. You also reduce the amount of RF noise that's being injected into the analog section. That's important from a distortion point of view. It's also very important from a noise floor modulation point of view. Now, there are lots of different types of multi-bit delta sigma. But we can talk about three main types. There's the unitary type, which is multiple elements of the same value. Then we've got the PWM output. And finally, we've got my own pulse array. So, unitary value. This uses a number of the same elements. So, for example, a 5-bit DAC would use 32 different elements. They're all the same value. So if you wanted 32 elements to reproduce 0, you'd have 16 being on, 16 being off. And as you increase the level, you just simply increase the number of elements you've got switched on. The simplest way of doing this is to use something called a thermometer DAC. And here you have 0, 1, you switch 1 on, you switch 2 on, you switch 3 on. And you don't worry about anything else, you just turn them on a simple way. The problem with this approach is element mismatch, because we're back to R2R resistors, and each individual one will change the gain, that will change the linearity, so you're going to get lots of distortion from this. So you can reduce this by rotating the element selection. Just simply move on to the next one. That way you're averaging the problem. That still creates distortion, and it also creates noise as well. A better way of doing it is to use something called, there's another way of doing it, and that's to use a random multiplexing. So you randomize which elements you're using, but that still creates some form of distortion. The best way of doing it is to actually use a secondary noise shaper, and each element is being noise shaped, and they're selected depending upon what's happened in the past. That way you optimize the performance. But all unitary value techniques have got these fundamental problems. Noise floor modulation is an issue because your switching activity depends upon the signal. And you don't want switching activity, your glitches, to change with the signal level, because that will create distortion. The other problem with it is that the noise shaper is limited to 64 or at best 128 fs. So 128 fs is 6 megahertz. So this means that the small signal performance is being limited because the noise shaper is running at a fairly low rate of 6 megahertz. Also, you cannot get nanoseconds worth of transient reconstruction because you're looking at something that will only resolve a few hundred nanoseconds, not tens of nanoseconds. So, a better approach, and this is something I've used myself in the past, is to use pulse width modulation, or PWM. That's exactly the same as Class D. In this case, you'll have the noise shaper running at 64 times fs, or 3 megahertz, and you'll have a master clock running at 98 megahertz, and the PWM waveform is has the noise shaper data embedded in it. So long as you ban 100% modulation or 0% modulation. The beauty of PWM is that it's a fixed switching frequency. So the glitches that you get when you switch it become like a DC offset. So it doesn't create switching noise, which you have the big problem with R2R DACS and with the unitary delta sigma. There's no element mismatch distortion because you've only got one element. And if you decide you want to improve performance by using lots of PWM and summing them together by delaying, they are still each handling the same signal, the audio signal, so there's no mismatch issues. So that's a very good way of reducing distortion. But PWM can be sensitive to jitter because the signal is constantly going from fully positive to fully negative. So that's a source of jitter sensitivity. So you can get excellent, really, really good measured performance from PWM. But it suffers from a fatal flaw. So this is a PWM waveform that I pinched off the internet. If we look at a 50-50 duty cycle, 50-50 is when you're reproducing 0, and let's say you want to go negative, -6 dB, then the pulses here, you can see that pulse there is later than this pulse here. This edge here, that's later. And on the other side, if you want to go to 100% modulation, this edge is earlier. So the problem we've got, as this signal becomes more positive, the transients become earlier. And this is a major source of transient reconstruction errors. If you filter the output of the PWM, that won't resolve the problem because it's innately there. And the amount of filtering you would need to do would be a sync function type filter, which you can't do in analog domain. So this will modulate your transient reconstruction. Transient timing is an essential psychoacoustic cue. We use transients, or the brain uses transients for timbre, for instrument separation, for pitch, particularly bass pitch. So if you mess up your transient timing, you're going to degrade all of that. And this is something I'll be talking about in much more detail tomorrow when I'm talking about interpolation filters. So when you degrade the transient timing, the timbre variation, instrument separation focus, pitch, and of course the starting and stopping of notes become degraded. And when I've listened to my own PWM DACs, many years ago when I was working with them, and I've used them for low-cost chip design because they're a very easy way of creating a low-cost, high-performance DAC. They tend to sound clinical, analytical, and lack musicality. That's my own personal opinion, of course. So what I've been talking about so far is conventional DACs. And that's as accurate as I can make it. There's nothing about what I'm trying to do. So now we're going to start talking about pulse array. So the first thing I need to say is, what do I want to accomplish with a DAC design? And what I'm trying to do is to recapture the emotion when you listen to a live acoustic event. It's very easy to get emotional. And when I'm reproducing my audio, it's not as emotional as a live event. So what I want to do is to improve the musicality, and I'll define musicality as being able to get emotional. The spine tingling thing, tapping your feet, wanting to listen to music for eight hours, wanting to listen to different music. These are all things that are affected by musicality. Now, most DAC designers want to create a particular type of sound. So they may want a very bright analytical sound, or they may want a really rich and warm sound. So they're turning their DAC into a musical instrument with its own flavour. Now, if you happen to like that flavour, then that's fine. I'm not going to argue against that. If that's what your preference is, then fine. The trouble with this approach is that every piece of music will sound the same because the signature of the DAC is becoming the sound that you're perceiving. I want the variation that you get from live music, unamplified music. Variation from live amplified music, it can sound incredibly hard, bright, aggressive, and painful. It can also sound really rich and smooth and soft. And I want my gear to be able to portray those changes. So, what do we need to do to reproduce musical involvement? Because it's all very well saying, I want to maximize musicality, I'm getting emotional. But you weren't there when you did the recording. You don't know what the mics were. You don't know what the mixing desk and the mastering engineer was doing. You've no idea what the original sound was. So how, as a designer, do I get a clue as to whether I'm making an improvement or just optimizing the sound? The key is variations. If you get more variations in timbre, variations in space, dynamic, instrument separation, and being able to perceive the starting and stopping of notes, if the DAC is becoming more varied, you know you're getting closer to the original musical truth. The only way of achieving this is through true transparency. I say true transparency because it's very easy to fool the ear into thinking that something sounds more transparent because it's giving you enhanced sound quality, a sharper sound, but it's not natural. And the only way of actually recognizing that you're not hearing true transparency is if it's more emotionally involving or not more emotionally involving. So, designing for high-end audio. We've got no understanding how the brain processes the ear's data. Most designers look at the performance of the ear and say it's 1% distortion or whatever, 90 odd dBs dynamic range. All we need to do for a DAC is to exceed the performance of the ear, job done. That actually, it sounds like a fairly rational way to go. You know, why make something better than the performance of the ear? The problem with this is it ignores the effect of the brain and what the brain is doing in processing the sound. And when you look at psychoacoustic tests to evaluate the performance of the ear, they're only looking at the ear. They're not looking at how the brain is functioning. It's not looking at timbre variation. It's not looking at depth or soundstage. Audio chips are designed by simple technical performance. So someone comes up with a spec, the designers have to meet that spec. It's not about listening tests. And you can't make any assumptions as to whether something will make a difference to the sound or not. The only way you can do it is to do a very careful listening test and to evaluate whether an error, identify the error first, and then evaluate whether that error makes a difference to the sound. And then you have to go through the process of making that error small enough so you can no longer hear a change. When you can no longer hear a change, that's perfect, because there's no question about interpretation or whatever. You've solved the issue. So it's vital to correlate errors to sound quality. So this is a situation that I had with a particular company. They bought my IP and my patents. They wanted to embed the IP into the company so that they could say, wave bye-bye to me and get on with it. We kept on having arguments about this needs to be done this way because it sounds better. So I did a simple test with a noise shaper that had 180 dB performance, which to anybody's technical guy would be perfect. against a noise shaper that had 200 dB performance. Got one of their engineers down, did a listening test. He could hear a difference. And he said it to me afterwards, I could hear the difference, and I knew that what you were saying was correct, that there would be a difference. What surprised me was how easy it was to hear the difference. So these very, very small differences can have a very major impact on performance. So what technical factors contribute to true transparency? We've got to worry about distortion. We have to worry about small signal nonlinearity, because that's very important for depth and detail resolution. We've got to worry about noise floor modulation and transient timing reconstruction. And that, as I mentioned earlier, is covered in my seminar tomorrow. Recent listening tests that I've done on transient timing, it doesn't matter how small the errors are, they are perceivable. And it's pretty crazy how small the errors that we're talking about. So what levels of distortion is audible? Higher order distortion is a massive problem. And anharmonic distortion, that is distortion that is not harmonically related to the input signal, that is also a big problem. Generally, if I see something that's measurable, then it will have an audible consequence. So if you reduce that distortion, you'll get a sound quality benefit, assuming you haven't changed anything else when you've done that change. And that's a big assumption, by the way. So I generally go for 24-bit performance, so that as a target, harmonics should be below minus 144 dB. I don't know whether that's the ultimate limit, because that's pretty much the best that we can do at the moment, or I can do at the moment. Curiously, out-of-band distortion can be very audible. Now, this is pretty weird to think that distortion at 250 kilohertz can have an audible consequence. But one time I had a problem at that level, reduced it, and you could hear the difference in sound quality. The mechanism for that is not that we can hear 250 kilohertz, but the effect of high-frequency distortion changes your timing of transients. And if that happens, then it becomes perceivable. Depth is a major bugbear for me. If you go to a cathedral and listen to an organ, if you're 200 feet away, it sounds 200 feet away. If you listen to your reproduced audio on headphones or on loudspeakers, it doesn't sound anything like 200 feet. And that's something that, I'm constantly working on. What I found is that small signal nonlinearity really is crucially important. And one of my tests is to use something called a minus 301 dB signal. So all my digital parts are tested in simulation with minus 301 dB. If there's a slight error within a thousandth of a dB, it's audible. If there's an error in the phase compared to 0 dB, and here we're looking at a thousandth of a degree in phase, you can hear the difference, which is pretty damn staggering, because it makes no sense that we need this level of accuracy. So again, no matter how small the error, it's audible. So, and the reason I know this is important subjectively is that when I was developing Dave, I had 200 dB noise shapers. That was what I considered to be the best. Who needs better than 200 dB noise shapers? And with Dave, I went from 200 to 220, heard an improvement in depth, and eventually went from 330 dBs performance to 350 dBs performance, and you could still hear a tiny improvement in depth perception. So that's how I know that testing for minus 301 dB is actually important. Noise floor modulation. Now this is a very, very important concept. All DACs create noise, and a fixed noise is perfectly okay, it doesn't matter. But if that noise changes with signal, then you're in trouble. And this creates noise floor modulation, and it has a number of different subjective effects. So large levels of noise source modulation, you're looking at a grainy treble. Smaller levels will change your perception of refinement or smoothness, and it will change your timbre variation as well. So having a bright instrument sounding bright and a rich instrument sounding rich, that noise source modulation plays a part of this. Again, levels below measurable levels are still audible, and even ultra small errors are audible. So, getting on to pulse array. This was invented in '95, and the intent was to make it sound as good as DSD-256, but solve all the other problems that DSD has got. Since then, I've improved pulse array because my knowledge about what we need to make it transparent has changed a lot over the last 25 years. Pulse array is the only DAC conversion technology that looks at transient reconstruction, small signal accuracy, and noise source modulation. What it is, it's an array of discrete flip-flops and resistors. They're all PWM signals on the pulse array, and what I've got is a rising edge balanced by a falling edge. That means that your jitter sensitivity is reduced. It's also, as it's PWM, a constant switching activity. So we don't have any problems with signal correlate glitch noise causing problems. The other benefit I've got with pulse array is that when you shut the DAC down, so you feed each individual elements with DC, the noise only changes by half a dB. And that means that your intrinsic switching activity is not changing the noise performance. It's all down to the resistor noise and the op-amp noise. And that's very important. So, noise shapers, I've talked about this as being really important. And the benefit the pulse array has got is that you can run the noise shaper at 104 megahertz. We can actually put 52 megahertz in as a signal and it will reproduce it. It ain't going to be very good. It'll be about 1% distortion and noise, but it will physically reproduce it. The benefit of running 104 megahertz means that the digital domain performance, I'm not talking about the measured performance, I'm talking about the digital domain performance, which is a measurement. It's the actual performance digitally. It will reproduce a minus 301 dB signal with perfect amplitude and perfect phase shift. There's no noise source modulation in the noise shaper as well. And as I mentioned, it can reproduce 52 megahertz. There's no observable on simulation transient timing errors. And by observable, I mean looking at signals with transients at 10 nanoseconds. I can see no change in transient performance. So we haven't got the DSD transient small signal problem. The other beauty of pulse array is it allows for a very simple analog section. My DACs are very strange because I do the complete opposite of everybody else. I have an extremely complex digital section in order to get the best transparency. And I have extremely simple analog section in order to get the best transparency. And actually they're interrelated mathematically, because every time you have a metal-to-metal contact, your small signal gets degraded. That will degrade your depth of perception. So it's very important for analog to keep it as simple as you possibly can, because that improves transparency. Unfortunately, analog engineers know this issue, and they think, well, digital must be the same. Let's make it simple. And that's not the best way for transparency. For transparency with digital, you need to make it very, very complicated. You wouldn't believe some of the things I've been up to recently with very huge FPGAs. I've only got 2 resistors and 2 capacitors in the direct signal path. This is because running at 104 megahertz means that the noise level at 1 megahertz is actually very low. That means I don't have to have a complicated filtering section. It's single-ended, it's not differential. Conventional DACs are differential. You have a positive output and a negative output. You then have two sets of I2V converters. You'll then do a differential to single-ended converter. You'll then have an output buffer. Lots of analog complexity, lots of amplifiers. With mine, it's just one amplifier that's capable of driving headphones directly. The amp itself is actually very sophisticated. It uses noise shaping techniques. It's a second-order analog noise shaper. The beauty of this is that you can eliminate high-frequency distortion. You can also eliminate crossover distortion. So when the Class A-B output stage switches into Class B, there's no high-frequency distortion at all. And when you load it, like a TT2, for example, when you load it, you see no change in distortion characteristics. So you can put a 300 ohm load onto a TT2 running at 9 volts, drop down to 8 ohms. The only thing that will change will be your second harmonic. The higher order harmonics will not change at all. Right, I've managed it. So we've got some time for some questions, which I always think is the most interesting part.
So I would like to know how you do your simulations, what tools you use.
Okay, so it depends what you're simulating. So if it's a digital circuit, you'll use Verilog. The Xilinx tools have got a Verilog simulator built into it. So you do a behavioral simulation, and what you get, so long as the place and route is being done correctly, the output from that will be identical to the hardware implementation that you actually do. For other simulations, it'll be Spice for analog stuff, MATLAB I use, and sometimes I do my own models in Excel, which actually I find is quite an easy way of doing things. But 4 million points on an Excel spreadsheet is a bit of a pain. Yeah?
What would be the challenges involved in designing a circuit that could accommodate more than one DAC, such as like a pure DSD DAC to decode DSD files and then a PCM or like a stealth signal?
Okay, so the problem with DSD is that you've got this large levels of noise. 100 kilohertz, you're looking at minus 20 dB. That's DSD 64. If you try and feed that into an analog circuit, it's going to either overload or it's going to create noise floor modulation, because that will go into the I2V converter and create nonlinearities. So you want to remove that. By removing that, you're filtering. By filtering, you're converting it into PCM. So there's never an argument for keeping DSD and running it as a DSD-only DAC. It's better to filter it correctly and then use it as regular PCM. Another benefit of doing in PCM, you can do EQ. You can do the crossfeed, which you can't do with DSD. You can do a volume control. You don't want to do a volume control in analog because that just increases problems. My volume controls are completely transparent because they meet the 301 dB pass, the test for that. So yes, there's a whole set of reasons why you don't want to do that.
But why then capture audio in DSD at all if it has to go through a conversion?
I wish they wouldn't. So, one of the projects that I'm working on is my own pulse array A to D converter. One of the reasons why I was having to do this presentation at 1 o'clock in the morning today was I've been so busy testing out various different things, one of which is a pulse array A to D converter. And I'm doing my own recordings. The benefit of doing my own recordings is I can compare reproduced sound to the sound I've got actually when I'm there, sitting below the microphone, so you can get a real solid reference on what's going on. And that's been really valuable. Any more questions? Yeah.
Any recommended readings?
Sorry?
Any recommended readings on the topics?
Oh, gosh. Yeah, read my postings on Headphone.
We can look up your patents, can't we?
You certainly can, but that's not going to tell you much about DACS, and it's certainly not going to tell you about interpolation filters, because I didn't sell them that. No, all the modern stuff is, I mean, the things that have changed for me over the last 10 years has been enormous. And I stopped working with semiconductor companies in 2015, and the things I've learned since then have just been staggering. I'm so delighted because the improvements I've made for me to enjoy music has been huge. And people often come up to me and say, "Oh, thank you very much. I'm so delighted with my Mojo," or whatever. I'm enjoying my music more. And I think, yeah, that's what it's all about. That's what I've been doing on this thing. And I've been lucky that, the last 10 years, I've seen huge changes in performance. That's partly because of time, and partly because FPGAs have become much more capable over the last 10 years. So you can do some really interesting stuff and explore things that you could never explore when you're limited to 20,000 gates. Now we're limited to 1 million gates. So it opens up so many different things to try out.
One more question. Since
Sure.
you're talking about how much you enjoy music through these things, what amplifiers, what speakers, what sources
Okay,
do you listen to?
so-
What kind of music?
I listen to lots of different music, mostly classical music. Recently I've been listening to a lot of modern day composers. The names escape me, so I always get asked this question, and my mind goes completely blank. Who I was listening to on the flight over, it's Richter, Max Richter. I really love that composer. So in terms of headphones, I use Dan Clark Stealths. They are extremely good headphones, and I know because we use them when we're doing our recordings, and so you can hear the sound of the Stealths and then listen to the actual music itself directly, and they were surprisingly much closer than I expected them to be. And for loudspeakers, it's B&W 803s, for which I use my TT2 to feed directly with the 7-watt output.
Unfortunately, we're out of time, but please join me in thanking Rob Watts.